So for our spread spectrum, let me go to this waveform. Our message that we will modulate and demodulate, transmit by a spread spectrum will be a 2 kilohertz sine. Our spreading sequence will be this pseudo-random sequence, which we are clocking at 100 kilohertz. So if I look at the spectrum, so the blue line is the spectrum of our message, and the red is the spectrum of our spreading sequence. So to create this direct sequence spread spectrum, what I'm going to do is I'm going to multiply two kilohertz sine with the spreading sequence. So I have two, let me go back to time domain. So I'm going to multiply 2 kilohertz sine with the spreading sequence, and that gives me, in the time domain, a waveform like that. Now, I don't think anyone can tell you what a direct sequence spread spectrum waveform looks like in the time domain, but in the frequency domain, now we can see what our spread spectrum signal looks like.
Yes.
So now, let me demodulate this signal. I'm going to take this module, which is our quadrature utilities, because it has two independent multipliers and an independent adder. I'm just going to use this top multiplier. So I'm going to take the spread spectrum signal and put it to one input of the multiplier. I'm going to take the same sequence that I'm using as the spreading sequence, so I'm going to steal that to simplify the experiment. I'm going to steal that sequence, multiply it, and go to the time domain. So there's the sequence, there's the direct sequence spread spectrum, and there's the demodulated spread spectrum. Now you can see it has a lot of noise. If we go to the spectrum domain, here you can see there's a lot of noise.
Yes.
What I'm going to do now, and this you'll see, the next two steps will be quite fascinating. I'm going to take this and pass it through a low-pass filter. Now let me just go back here. So
it will be much clearer. Yes.
So our blue is the original message. The red is the recovered spread spectrum. What happens if I use a different sequence at the demodulator? This looks interesting. It's not measurable, but let's look at the spectrum. And let me zoom in. So do you see the red? If I go before the filter, there's our spread spectrum. If I go after the filter, obviously what we can see is whatever I'm tuning, this is a tunable low-pass filter.
Yes.
But what we're seeing is the noise. Watch what happens when I change it from a different sequence to the original sequence. So there you can see the red coming through, and the noise is now 55 more, 60 dB down. So with this simple demonstration, we can explain and show to students the way spread spectrum works is each, for example, cell phone, mobile phone, has a different code. And that's why if there are multiple phones in the same area, because they have different codes, they don't interfere with each other. And here is a simple demonstration of correct code, wrong code.
Yes.
Wrong code, correct code. And you can see that from that spectrum, from all those harmonics being transmitted, when you have the correct code, it falls into place. And this is the simplest of demonstrations of spread spectrum.
Yes.
So this is my my very quick digital modulation scheme. So even though it's more advanced, in a sense, it actually shows you that it's quite simple. And just to explain to you, when TIMS was first released, there was no interest in spread spectrum, but we did have this core experiment in the back of one of our lab manuals. And some 5 years after, 5 or 10 years later, we started being contacted by universities who are asking, tell me about this spread spectrum experiment, because now it had moved from the US military, from NATO, into the commercial world. So now universities wanted to start to demonstrate the principles of this new technology called spread spectrum. And the most important point is that when they purchased TIMS, they had no need for spread spectrum. Years later, they could implement it using the blocks that were included in the basic system. No new modules were required to implement a completely new modulation scheme because the building blocks were already there. So that again ties up with my explanation and my concept that TIMS is actually a modeling system, and it's up to how you wish to teach in terms of range of experiments and depth of experiments. TIMS gives you that capability. That's why TIMS is a true hardware modeling system. So with that,